Hi guys, now I would like to look for the optimizations on the model built based on the individual assignment 1. So I've got the model ready. You see that I included pie diagrams for each element in the model, so I can evaluate the model easily. I have added also a variable counting the production, so we will see the performance of the model always after we stop the model. At this moment, I've got 1000 minutes set. I'll do the batch run. And in our base scenario, within 1000 minutes, the production is 227 minutes. And for example, I see that the worker is busy almost all the time, but there's still some fraction which the worker is idle. If I want to see that exactly, I can go here under type, I'll click on labor, right click, check statistics, check swap rows and columns. I see that he's about 2.5% of the time idle. In this particular model, that's caused mostly by the beginning of the simulation. Since I know already that the worker is gonna be busy almost 100% all the time. So this is the case where the warm-up time would help to make the statistics more precise. So here, what I'll do is that I'll include warm-up time of 50 minutes. Since I know that that's a time when the first product is out of the process quite for sure. If I want to check whether I'm correct about the warm-up time, I can set 50 minutes here. I reset the model, I run the batch run, and I see that after 50 minutes already 10 pieces have been produced. So it's in this case safe warm-up time 50 minutes. So I'll add the 50 minutes here. I'll make it 1050 here. I'll reset the model to 0. I'll do the batch run. We see that the stats for the worker, but also for the other elements are different now. So I check the stats for labor and only 0%, 0.7% of the time the worker is idle, otherwise it's busy almost 100% of the time. Also, we see that the production has changed from 227 to 242. That's as well the result of the different warm-up time. And for further simulations, I'd like to use the simulation time of 1 month period. Let's say that in our company, the 1 month is a reporting period. So in reality, we'll be interested in numbers after 1 month time. That means in case of our country, we have 8 hours per day. In our country, each hour has 60 minutes. And say it's gonna be 20 days per month, which makes 9,600 minutes. And let's keep the warm-up time of 50. So let's enter 9,650 here. So that's the simulation time we'll be using. Actually, our model is stochastic. We're using the user-defined distribution to govern the breakdowns. How long do they take? Breakdowns of machine 04. And if we want to repeat how to work, how to set the minimum simulation time for stochastic models, we know that we should allow the stochastic event to happen at least 15 times during the simulation. And since we know that it happens each 50 operations, and we should calculate how often the operations happen. So we've got in 1000 minutes, we've got approximately 200 products out. That means about 5 minutes per operation. 50 operations multiplied by 5 is 250, and we want to allow the event to happen at least 15 times. So I multiplied by 15. This should be the sufficient minimum simulation time. It's lower than our reporting period. So if we use our reporting period, then we are safe because we're fulfilling the conditions we have set. If our model was deterministic, there was no probability, then it would be okay if we used even lower number than the 3760 minutes we just computed. I'll confirm okay. Now I'm ready to run the simulations. I do the batch run, and our base case scenario now produces 2263 products per our simulation. Let's evaluate the model, what to optimize. Here it's quite easy. If I look first at the machine 01, I see that it's either working or being blocked. Since it's being blocked, it means that the problem is past machine 01. The next element is machine 02, and I see that it's either busy or waiting cycle labor. Okay, so this is the color, wait cycle labor. I can check the stats as well. It's waiting more than 50% of the time it's waiting for the worker. That's caused by the fact that the worker not only has to operate the machine 02, but also attends the setups at machines 003. So whatever I do on any other place within the model, if it's not about this place, it's not gonna help the production. And since it's the worker who are we waiting for all the time, we need to double the number of our workers. And we see also here that the worker is almost 100% busy. So whatever we do anywhere else, it's not gonna help. If I continue, if I started, for example, evaluating the model from the end, I would look at the machine 04 and I would see a lot of idle time. That means that the problem is before machine 04. Machine 03, it's being blocked for some part of the time. It means that some problem is past machine 003, sorry, but still there's some fraction of idle time. And if we continue here, we see that it's idle because the machine 02 is not able to provide enough material for machine 03. So I go to specification of workers. I will double their quantity. I'll confirm it OK. I'll reset the model to 0. I'll do the batch run. And I see that the production has changed to 2470. I could have actually expected that, since I'll show the previous numbers once again, since I'll be working with one worker now. Here I see that if I optimize this this place, then most likely the next bottleneck is going to be somewhere here. And since I see that the machine 03 I see if I check the stats, I check the stats of machine 03. I see that they're idle about 7% of the time and waiting for the setup labor about 1%. So the potential, if we add a laborer, the potential of improvement is about 8%. And 8% of 2263, it's about 200. So I double click worker. I double the quantity again. I do the batch run. And I see it has changed about 200 pieces. So after our first optimization, where the bottleneck has moved. If I start from the front again, machine 01 being blocked, the problem has to be past machine 01. Machine 02 blocked a lot as well. Machine 03 being busy or being set up or being blocked. So again, the problem has to be past machine 03. But machine 04 has a lot of idle time. So this is tricky at this moment, and the problem is that we see that the process is being blocked for some time, but still machine 04 has a lot of free capacity. How is that possible? The machine 04 is broken down almost 25% of the time, maybe about 20% of the time. In such case, the conveyor 02, we know that that conveyor is the fixed type, and if machine 04 is blocked because it's being broken down, the conveyor 02 can't feed the machine 04 and has to stop at that moment. That means that the first part on conveyor 02 will reach the end of the conveyor, can't continue, so the whole conveyor has to stop, even though that we've got large spaces between the other parts on the conveyor. That's the fixed type of conveyor. On contrary, conveyor 01, it's the queuing type. That means that if this part has to stop, the other parts can pile up just after, just behind, and it works like kind of a buffer. In this case of machine 04, the conveyor 02 stops. When the machine 04 is repaired and starts operating again, this part enters the machine 04. The machine 04 is quite fast, so it ends the cycle very fast, produces the product. And then the machine 04 is just waiting till the other parts travel till the end of the conveyor 02. What could help would be turning the conveyor into indexed queuing, so the parts can actually pile up as on conveyor 01, and it will act as a kind of a buffer. So let's check whether it helps. I'll reset to 0. I'll do the batch run. Now the new production is 2,806 products. So we see that it helped. It helped a lot. What's the next bottleneck? Or once again about the conveyors. Just a minute to get back to the conveyors. Of course, changing the type of conveyor has to conform to reality. If it's possible in reality, we can do it. If it's not possible, we can't. And okay, let's have a look at the process at this moment. So I'll start from the front again. Machine 01 blocked for some part of the time. Machine 2 blocked for some part of the time as well. Machine 03, it's blocked a little, it's being set up, and it's busy a lot as well. We see that the machine 04 has still a lot of free capacity, so the machine 04 is again not the bottleneck. At this time, it's going to be the machine 03. It's being blocked a little, but it's the least percentage out of all the elements we've got here in our process. So let's double click machine 03. I'll increase its quantity to 3. I'll confirm with OK. Now we need to check that all the machines are connected both to the previous element and both to the next element. I will reset the model to 0. I'll do the batch run. And the production has increased once again. 3,203 products now. What's the bottleneck now? If I start from the back, machine 04 still has some free capacity. Machine 03 as well, free capacity. Machine 02 still free capacity. So the problem is before these, the machine 01 is almost 100% busy. I can check exact statistics. 99.92 busy time. So at this moment, the bottleneck is machine 01. I'll reset the model to 0. I'll increase the capacity or the quantity of machine 01 to 2. Once again, I check the arrows and I do the batch run. And yes, the production has increased. And this way you can continue further and further with the optimization steps. Maybe you will see again that there's a problem with the machine 04 blocking. That would be probably the problem at this moment, blocking all the previous elements, even though that we've changed the conveyor 02 into the queuing conveyor. If you observe the simulation in slow motion, that means you switch on this little guy, you adjust these speeds, and you observe the model for sufficient time, you would see that even changing the conveyor into the queuing type sometimes does not help. The machine 04 stops the whole process, the conveyor 02 becomes full, everything else has to stop, and then the machine 04 produces so fast that nevertheless it still has free capacity, even though that it blocks for some time the whole process before. So let's try to confirm this assumption. I will include a new buffer here, and I'll make the conveyor using this buffer. The machine 04 will pull from the buffer. I'll confirm with OK. Okay, the buffer is connected. I limit the size to, let's say, 100. I'll confirm with OK. I'll reset the model to 0. And the production has increased to 3725. This moment we got to the very same situation as at the beginning. The machine O2 is all the time either working or waiting for the laborer, even though the workers are not busy 100% of the time. They're still being the bottleneck of the model. So the next step would be adding a worker, confirm with OK, trying, and the production has increased a bit. Now, at this moment, this is a bit specific situation. At this moment, we see that machine O4 free capacity. Buffer O2, it's not full at the end of the simulation. Machine O3 free capacity, machine O2 free capacity as well, machine O1 a lot of free capacity. What's the problem now? All the elements have free capacity and the production is only 3848. We see that the buffers for incoming parts are empty. That means that the problem is that we are not getting enough material for our model. The next optimization would have to be outside of our model because we are not getting the material fast enough. Okay, I'll stop the simulation now, or I'll stop the recording now, and I just saw one problem, difference to your models, or difference to the assignment. The part 002 was supposed to be coming faster than the part 001. So actually this problem of insufficient material supplies would appear if the model was correct. That would appear a bit sooner than now. Okay, so you can check with how it works, the optimization steps with this tutorial and with the correct model. So have fun and be well.